So this talk will be on, I'll be talking about privacy, not surprisingly, and privacy is sort of for statistical data. So this is a bit of an abstraction of a few settings we've heard about this morning. So imagine we've got an agency, maybe the Census Bureau, maybe someone trying to organize an open data data sharing platform that has or collects data from a bunch of individuals and would like to make these data as available as possible for research. Okay, so there's this basic tension here between allowing as many different types of queries to the data and sort of providing as detailed answers as possible, and providing privacy or confidentiality guarantees to the individuals whose data we collect. And of course, large collections of sensitive information are ubiquitous. So there's the census, there's data from every other kind of walk of life you could think of. These are types of data where statistical analysis or access to these data at this sort of broad statistical aggregate level has real societal benefits. But as we were mentioning earlier today, the thing that makes these data valuable is exactly what makes them sensitive, namely that they paint very detailed portraits of our lives. So we're sort of trying to understand these two conflicting goals, utility on one hand and privacy on the other. Okay, so I'll argue that utility is sort of the thing we're used to thinking about. So this came up in the talk this morning, that we need measures of utility for various reasons. But arguably this is the central question. Understanding exactly what utility means is the central question in many fields, statistics and machine learning and many areas of the social sciences. Basically any area where you're trying to draw inferences from data, people will generally have carefully thought about what it means to get useful information from the data. Privacy, on the other hand, has traditionally been less well understood. And so really the question that will sort of animate the talk and that I think is sort of topical for this workshop is, what do we mean by privacy in these statistical settings? Okay. So this is not a new question. People have been thinking about it since the 1960s in statistics. But since roughly 2003, there's been a real push from computer scientists to put this on more rigorous foundations, and I'll be talking about sort of one branch of that line of work. Okay, so just to address something that came up this morning, the sort of straightforward thing you want to do, say you've got a bunch of data and you want to make it as available as possible. The sort of obvious first thing you could do is to look for anything in the data that's obviously identifying, things like names and social security numbers and exact addresses. Just remove those, right? De-identify the data, and just publish whatever's left. And there are a few problems with this. Sometimes, one problem is sometimes the thing you're interested in is how it actually concerns these sort of identifying features. So for example, if you're trying to if you're looking at a disease outbreak, you might need to know exactly where people live. The exact addresses might really matter. That might be the thing that you want to study. And the other problem is it doesn't really work. So for example, consider the following image. So this is a person. We've grayed out his face to make him hard to identify. But most of us can identify this person reasonably quickly, perhaps with a pang of nostalgia, because there's all this other information in the photograph.
It's the ears.
It's the ears, right. There's all this other information in the photograph that that we can interpret, that we can connect to other sources of information to narrow down the how many the number of possible people who could be standing there, and eventually figure out who it is. Okay, and obviously this is a toy example, but there are lots of examples in the research literature on, and indeed in the press of sort of examples of where this type of naive attempt at de-identification has failed. Just to give you a few examples, one related to this toy example is that you can sort of, there's various software for blurring faces, but in fact, if you train face recognition software on blurred images of a person's face, then you will be able to use it to recognize blurred images of that person. There's an example where people looked at genomic data from which names and all demographic information had been removed, just the basic genomic sequence was left. And it turns out that from such data, you can predict men's last names with reasonable accuracy. And that's because most men in Western society inherit their last names and Y chromosome from the same person. There was a kind of an example of a taxi data set a few years ago where people were able to, this is New York City taxi data that was sort of supposedly anonymized and didn't take too much effort to sort of quote reverse that anonymization process and sort of figure out some specific riders in some of these these cabs. And I have some work that I'm not going to talk about. Anyway, so just some like simple lessons from these types of examples, of which I'm giving you only a few, but there are many more. Everything's an identifier. So it's really hard to distinguish personally identifiable information from non-identifying information. Anything that really carries information about people can, in combination with other things, be used to identify them. We should be reasoning about not only the data sets that we know about currently, but data sets, other sources of external information that might be available in the future that we don't know about. Again, this came up in Arif's talk this morning. Anyway, as a result of these sort of straightforward attempts at anonymization of relatively complex data are broken on a semi-regular basis. And so the lesson I would like to draw from this, that I'd like you to remember, is that de-identified data is not. Okay? Anything that is sufficiently rich it can, in combination with other things, identify a person. And so while the concept of re-identification and de-identification is important and interesting, it's a bit of a red herring. So I don't want to say we should throw it out completely, but we need to understand that sort of mere compliance with existing regulations is not a sufficient goal to aim for, because those regulations are based on in many cases 20, 30, 40-year-old understanding of the sort of threats that we might face. Okay, so you might suspect that based on the examples I just gave, that the problem is granularity, and that we'd be okay if we only release sort of aggregate level information about a data set, about people. Because in all those examples, whether or not it was obvious, in some sense one of the problems was that what was being released was information about individual level, like there was a mapping between individual records of the released information and real people. Okay, so there was it was meaningful to talk about re-identification. But it feels like if I release aggregate information, then there's no way it could be re-identified because it's not about individuals. Okay. And just to give you a sense of why that's problematic, the issue is that this notion of aggregate is much harder to pin down than you might at first suspect. Okay, and really what's going on is that many statistics taken together can encode data. Sort of a straightforward example that's easy to understand is, suppose I tell you someone's average salary immediately, not someone's average, I give you the average salary, let's say at a company, immediately before and after a particular person resigns from the company. Okay, so each of these salary averages on their own doesn't obviously carry a lot of information about any one person. But if I take these two averages and I know how many people work at the company, then I can figure out exactly what this person's salary was at the time they resigned. And this is sort of a simple example of a more general phenomenon, which is that, again, and it came up in RF's talk, but I'll repeat it, that if you've got too accurate statistics about a data set, even if they're sort of aggregate or apparently aggregate, then it is possible to reveal individual information. And this has been observed in practice in a number of works. It's been formalized in a couple of lines of work on so-called reconstruction attacks that Arf mentioned, and then on somewhat more recent line of work on membership inference attacks and what are called tracing attacks. And I'm not going to go into the details of what these are, but I will sort of try to draw a lesson from them, which is that, unfortunately, we're in this situation where even if we limit ourselves to aggregate types of information, if we've got a rich data set and we want to put information out there in the public domain, we're not going to be able to release everything everyone would ever want to know about a data set without basically releasing the data themselves. And so we're in this situation of having to make a choice, having to think about what exactly do we want to release, what do we not want to release, or how much can we release. And so we really have to understand this trade-off. And so we need tools to formalize that trade-off and reason about it precisely. Okay, so having sort of just set the stage, I'll tell you about a line of work on what's called differential privacy, which is sort of the idea is to define this notion of aggregate, define what is private in terms of stability of an algorithmic process, and I'll explain that when I get there. And it's a notion that's now widely studied and increasingly being deployed. As we heard this morning, it's influencing ongoing developments at the census and other places. We'll hear talks about it later in the day also. And then what I'll try to wrap up with and spend a chunk of time on is sort of what I see as interesting challenges that researchers can try to address that would sort of reduce the gap between what's going on in the research world and sort of actual applications of these ideas. Okay, so this is just first part of the talk. So this notion of differential privacy, it provides it's a notion of what it means for it's a definition that applies to the process by which we take a data set of sensitive individual information and create some sort of public use information. It provides rigorous guarantees that I'll try to explain against arbitrary external information, particularly resists the types of attacks that I had on the previous slides. And it's led to a burgeoning field of research with lots of stuff going on in lots of different research areas. Maybe the connections to different research areas are less topical today than sort of what is missing in terms of going just beyond doing lots of good research. Okay. Just sort of this is like random statistic that I have from this overview talk. Yeah, sort of recycled slide. Sorry, on how it's changed, how it's taking over the world. Okay, so. There are various differentially private algorithms that have been deployed. So Apple made a big deal about a year ago announcing that they would be collecting various kinds of information from iOS devices differentially privately. Google actually beat them to it and had been collecting information differentially privately from users of the Chrome web browser. And as we heard this morning, there's this sort of ongoing project at the US Census Bureau looking at the 2020 decennial census public use data products and trying to provide guarantees along the lines of differential privacy, not necessarily exactly what I'll present in this talk, but some other variants on the same basic idea. And this has also been applied for sort of trying to publish kind of more research data type products. There was a project that Rebecca was involved in on anonymizing data from cell phone calls, and another paper published last year by Jeremiah Blocky, Anupam Datta, and Joe Bono on a differentially private version of a password frequency data set. And these are just like random plots from those papers. So don't try to actually interpret them. Okay, so let me explain the definition. I'll try to be quick because I think it sort of, has come up a little bit earlier. But just to kind of make things more precise and also set the stage a little bit for some of the talks that are coming after mine. So hopefully I'll save some people some time. Okay, so here's our basic picture. Here's the agency. We're going to think of, we've got data coming into the agency. The agency does stuff with the data and produces some output. And what we're going to look at is the algorithm that the agency applies to produce this output. So the process that maps data to output. That process can be randomized, so that this agency may have its own source of random so-called random coins, like just a pseudorandom generator that gives it random looking bits that it uses to add noise, for example, or things like that. We'll think of the data set as fixed, though. We're not going to think of the data set as a random variable here. So we'll just imagine the data set is a list of values in some domain D. So it's n records from this domain, and the domain D could be something simple like numbers on the real line, or something complicated like tax forms. So for each person, for each of these n people, I have some data. And I'll think of x as I said, as fixed, not random. But the algorithm that's applied to it is randomized. And that means that this quantity a of x is itself a random variable. And this randomness might come from adding noise, from maybe subsampling from the data, various other types of things. And the basis of the definition is a thought experiment. What we'll do is we'll look at what happens if we were to change one person's data. So imagine we've got a data set x over here, and we'll get data set x prime by just replacing person number 2's tax form with some other tax form, arbitrary other tax form. And the question is, how much will the distribution on the outputs change? And the idea, that's going to be the basis of the definition. More formally, we'll say that two data sets are neighbors if they differ in one person's data, let's say one person's tax form. And that's what it means for them to be neighbors. And the requirement will be that neighboring data sets induce close distributions on outputs. So we're going to look at the probability distributions on outputs and how they change as we change the data. Okay, and here's the exact measure. So we'll say that A is epsilon differentially private. So this is the epsilon that came up in RF's talk. If for all neighboring data sets and for all pairs of neighboring data sets and for all possible subsets of outputs, the probability that the output lands in the subset when the data set is X is close to the probability that the output lands in the subset when the data set is X prime. And here close means off by a small multiplicative factor, and this epsilon quantity quantifies how far off those probabilities can be. So just a couple of quick notes. First of all, this is a condition on the process. It's a condition on the algorithm that processes the data. It's not that you point to a particular table and say that's okay to release, or this other table is okay, not okay. Right? You have to understand the actual map from inputs to outputs. And I think for computer scientists, that's a very natural way to think about it. Sort of, nevertheless, it was something that wasn't really all that common in the literature during the 20th century. What's this number epsilon? Well, it's some measure of information leakage. Remember, it was the x-axis in some of RF's plots. I won't really explain why, but the exact metric we use matters, and we should think of this number as small, but not too small. Okay, so 1 in 10 or 1 in 100 maybe, but not like cryptographically small. Okay, so I'll give you just one example of something differentially private, just so we have something concrete to think about. And I just want to stress that it is far from the only example of an algorithm. Like, not all algorithms that satisfy differential privacy look like this. But here's one thing you can do. Suppose that there's some function of your data you want to publish, some function you want to release. So one thing you could do is sort of compute that function on the data set. So suppose that function could be, some model parameters of some model you're trying to fit to the data, and you add noise. Okay, and you're going to publish that. So a really simple example could be, suppose I want to release the proportion of diabetics in the data set. So now for each person I have a bit indicating whether or not they're diabetic, and the thing I want to release is just the proportion of the bits that are 1. And a simple approach is, as I said, is to add noise to the function. The question is how much noise is needed. And it turns out that you can sort of get one approach to quantify the amount of noise that's needed is to look at properties of the function that would allow you to add a relatively small amount of noise. One such property is if you can bound a quantity called the global sensitivity. So that's the maximum over neighboring data sets of the difference between f of x and f of x prime. So it's a measure of how much this function f pushes apart data sets that differ in one person's record. So for example, the global sensitivity of the proportion function that I had on the previous slide is just 1/n, because if I change one person's diabetes status, then the proportion changes by at most 1/n. Okay, and then it turns out you can add noise proportional to this global sensitivity over epsilon, and this Laplace. So the result is that if I release this thing. So this is a random variable whose standard deviation is proportional to global sensitivity over epsilon. Then I get something that's epsilon differentially private. This specific distribution used here doesn't matter that much. It's the cleanest statement is from this Laplace distribution, which is kind of a pointy Gaussian distribution, but you can use other things. It just makes things a little messier.
Adam, yeah. One quick thing. So you no longer have randomness inside the A box, is that right?
No. Yeah. So here the randomness is going to be used to generate this noise.
Okay.
So here this Laplace random variable is sort of like this is the density function of the Laplace distribution. So it's kind of like a peaky Gaussian, and now you're scaling it. You're going to You're going to change the scale so that the standard deviation of the noise you add to each entry of f of x, if f of x is a vector, is proportional to the global sensitivity divided by epsilon. So the larger the more sensitive the function is, the more noise you're going to add, and the smaller you want the leakage to be, the more noise you're going to add.
Okay. But the function f is completely deterministic. There's no randomness.
No, not in f. That's right. And the basic idea, this theorem, such as it is not hard to prove. I mean, basically, if I look at the distribution of the outputs, when the data set is x, that's the blue density, and when the data set is x prime, that's the red density, and those are shifted by a certain amount. That is at most the global sensitivity, and so you just kind of have to understand how this distribution, how this density function changes when you kind of slide it around on the real line. Okay, so the only thing for this purpose of this talk, the only thing that you really need to extract from this example is that, well, one way to satisfy this definition is by adding a little bit of or possibly small amount, possibly large amount of noise, and that noise can be the amount of noise that it is sufficient to add is bounded above by this sensitivity quantity. And a lot of this basic idea is at the heart of a lot of algorithms that satisfy differential privacy, but not all. So there are actually lots of algorithmic techniques now that are known. There's noise addition along the lines I was just talking about. There's various kinds of sort of you construct various kind of funny distributions that you sample from using something called exponential sampling, or what's called a Gibbs sampler in some cases. There's sort of a set of techniques where what you do is based on using the data you have, you learn a much more succinct model of the data and then perturb that much more succinct model. There are various techniques based on subsampling and some sort of things that smell like bootstrapping. And I'm not going to go into, I don't have time to give you a whole survey that's like, the week-long course or something. But just to give you a flavor that there's a lot out there. Okay, so really? Really? Okay. I mentioned earlier that one of the things you get out of this idea, this notion of differential privacy, this restriction on the algorithm, is you get rigorous guarantees even against data, auxiliary data that you don't know at the time you're processing the data, the sensitive information. And I just want to explain that guarantee briefly, and then I'll talk about sort of some directions for possible future research. So naively, you might hope to get a guarantee of the following form. If you're an attacker or someone outside the system, and I'm a person whose data is in the data set, then I might hope to be able to say that your beliefs about me are going to be the same after you see the output of the algorithm, after you see the public output, as they were before you saw the public outputs. And it turns out that this is actually impossible to achieve. Okay, it's not achieved by differential privacy, and it's not really achieved by anything useful. And it has to do with the fact that we really are trying to release useful information. And sort of, I'll explain this with the parable of the smoker, if you will. Suppose that you know that I smoke, and that I've smoked for many years. And then you go and you see the output of the public version of some clinical study that tells you that smoking and cancer and certain forms of cancer are strongly correlated. Okay? From this, you will definitely learn something about me. What you learn is that I'm more likely than average, I'm at higher risk than average for these forms of lung cancer. And that's actionable information, right? You might deny me health insurance, you might decide not to hire me. So this is, you really have learned something about me from this clinical study. But that thing you learned about me didn't really depend on the fact that my data were used in the computation, right? It's just you're learning this fact about human biology, and that happens to tell you some information about me. So differential privacy implies that this is sort of the only kind of thing that can go wrong. It says that no matter what you, the attacker, know ahead of time, you'll learn essentially the same things about me, whether or not my data are used. Okay, so this is a guarantee. This is the kind of incremental guarantee we can provide. There's a lot of now research on differential privacy, as I mentioned, on definitional work, algorithmic techniques, various attacks and impossibility results, connections with other fields, and also work on specific applications. But this area of the research agenda, I think, is sort of underserved, and so I'd like to conclude with just a few comments about, is that like a -2 or +2? I've still got 2 minutes left, right? Good.
2 minutes left.
Yeah, great. Okay.
I'm not sure whether it's minus or plus.
All right. Let's call it, let's be positively minded and call it positive. Okay, so I'd like to just wrap up with some directions for research that I think are important, that really require conceptual contributions, but also have the potential to shrink the gap with application. Okay, and indeed that gap is substantial. Here are our researchers. Here are the people who actually do things. The researchers like me. We write these papers. You just have to understand these equations, and then your life will be okay, right? And everybody else is like, what? I don't speak Greek, right? And these puzzled researchers over here saying, why don't they just read my papers, right? Notice, every time you find yourself asking this question, you're probably engaging in some form of victim blaming, right? So, okay. So just some, things that researchers can do other than actually working for companies that are applying these things or government agencies. So one line of research that has begun, but for this there's still a lot to do, is developing statistical methodology for making valid inferences. Based on the kind of outputs of differentially private algorithms or noisy processes that add noise and things like that. And by valid inferences, I mean things like confidence intervals. So if you want, say, like you want to publish, you do some parameter estimation based on the output, and a typical thing you'd want to do is say, this is my estimate for my parameter, and here's a 95% confidence interval that gives you an idea of how accurately I feel I can estimate it. Right now, there isn't that much available for, if you go and implement various differentially private algorithms, it's hard to find guidance on how to provide all those other interpretive types of information, like confidence intervals and doing well-calibrated hypothesis tests, things like that. There's this question of various ways of modeling utility that came up in Arif's talk. For understanding the trade-off. If you're going to pick this epsilon quantity, somehow it's important to understand what you're giving up for a given level of epsilon, or what you're getting, and that's often not available or not very clear how to, at least not in terms that people who work with data directly need. There's issues about the local model. I'll come to that in a second. These algorithmic techniques that I mentioned, there's still a lot to be done on just basic algorithmic problems. And most of them have to do with, I would say the open questions have to do with exploiting particular structure that's present in a particular data set. So various constraints like structural zeros, or more interesting constraints that Arif mentioned, and basically designing more refined algorithms that really exploit the features of a particular problem. Another line of work that's important is understanding how to allocate usage and access to data. So one of the lessons of that early part of the talk is that we can't do everything we'd ever want to do with a given data set. And if we think of data as a public good, then suddenly there's this question of how do you decide which things you're going to release and which things you're not going to release, right? So you could have a central authority that makes the decisions for you. Okay. But history has shown that asking the people who are going to use something what they actually need is useful. And there are lots of mechanisms. Economists think explicitly about resource allocation. That's basically what all of economics is about. And bringing those tools to bear on this problem could be really fruitful. And finally, and this is sort of a big one, this could be a whole set of slide deck all to itself, is on sort of various other definitional approaches. So, differential privacy is sort of, as I specified, I gave you one little form of it, but there are a lot of variations, and it's potentially many more useful things that we could kind of require that would carry a lot of the same meaningful interpretation, but would be less restrictive in terms of the algorithm. Okay, so I did have more to say, but I'm going to skip this local model stuff. I'm sorry I didn't really have time to explain that, and leave you with this slide. All right, thanks very much.
I guess we have -2 minutes left. Question or two?
This one really isn't a question, so I'm going to address it this way. First, I'm going to take some credit, then I'm going to give a lot of credit. Differential privacy has been, I think, hugely influential on the research side already. It's starting to be practically influential as well. The taking credit part, I just want to say that DIMACS is very proud. The Dinor-Nissen work, the earlier precursor work, was done when they were both DIMACS postdocs. So we feel quite a.
It's true. We should have put the little DIMACS stamp on that one.
But also, Adam and his co-authors for the differential privacy work are going to be receiving, and this is not news to anyone, to you anyway, but they'll be receiving later this year the 2017 Goodall Prize. That recognizes significant work in mathematical logic and foundations of computing, theoretical foundations of computing. So